date. Just before I go into some background on Chris, could I just ask people who do have to stand today, could you make sure you're not standing any of the wires of our video camera audio equipment, because unfortunately we lost half of Tom Stonier's presentation yesterday because someone inadvertently stood on the wires. Which brings me to the point we are audioing and videoing this session today, and tapes will be available downstairs in the registration area if you wish to purchase them. Let me give you a background on Chris. Chris Date began his professional career in 1962 with Leo Computers in London, England, which is now, as we know, part of ICL. In 1967 he moved to IBM Hursley in England, and in 1974 to the IBM Santa Teresa Programming Center in San Jose, California, where where he was involved in technical planning for IBM database products. Chris actually left IBM in May '83 and is now working for himself. Chris has been active in the field of database, especially relational database, for some 12 years. He has made some numerous contributions to database theory and has published widely in the field. He is best known for his book, An Introduction to Database Systems, Addison Wellesley, first edition in '75, second in '77 and third in '81, so he's been keeping it up to date, obviously. And that is a standard text on the subject and is used in colleges and universities worldwide. More recently, he has published a sequel to that book, An Introduction to Database Systems, Volume 2, and that covers a range of more advanced aspects of database technology. Mr. Date enjoys a high reputation for his ability to communicate complex technical subjects in a clear and simple fashion, both on paper and in live presentations as today. As a result, he is in great demand as a speaker at conferences, seminars and the like. He has lectured widely on technical subjects, primarily on database topics, and especially on relational database, throughout the United States, Europe, Asia, Australia and Latin America. Mr. Date holds an honours degree in mathematics from Cambridge University, England, BA 62 and an MA in 66. He is a member of ACM, the ACM Special Interest Group on the Management of Data, SIGMOD, and the British Computer Society, BCS. Just before I introduce Chris's subject, slight change from our format to date. Rather than taking questions at the end and having the microphone in the middle of the venue, Chris is quite open to questions on the way through his presentation. And in fact, if you can just stand, identify yourself and your affiliation, company or government department, whatever. And Chris will actually repeat your question, mainly for the purposes of making sure that that question gets onto our videotape and contexts his answer. Just leading into Chris's presentation, database technology is a major growth area for the 80s, and much of the activity in the field is a direct result of the introduction in 1970 of the relational model of data. And it looks increasingly likely that by 1990, most people interacting with a database will be using a relational interface. Certainly there's no shortage of systems in the marketplace that either are or claim to be relational. In this presentation today, the speaker will briefly trace the developments that led to where we are today in this field, and will discuss some possible future directions for relational technology. The precise difference between relational and non-relational systems will also be explained. General headings that I could quickly put it under would be 3 generations of database systems, the basic relational model, current systems, what is a relational system, and topics for investigation. Now some of you may be saying that's quite different to what I read in the little handbook, and that is true. But that is exactly what Chris is going to talk about today. With no further ado, I'd like to introduce to you Mr. Chris Date.
Thank you, John. Can you hear me okay at the back? Wave if you can. Great. I hate these big build-up introductions, with all due respect. I was giving a talk in IBM a little while ago, just before I left, in Los Angeles, and the person who was introducing me there said to me ahead of time, "How do you want to be introduced?" And I said, "I hate introductions. Keep it as short as you can." Okay. We went down to the room. This guy, his name was Shelley, got up and said, "Good morning. My name is Shelley Weinberg. I'm here to introduce this morning's speaker. Here is this morning's speaker, and sat down. So, there has to be a happy medium somewhere. I'm very pleased to be here. I like coming to Australia, and I'm very pleased always to have the chance to spread the gospel, and that's what I'm doing, evangelizing a little bit. The background to this talk is that relational database has become a very hot topic. If you look at the product announcements these days, almost every announcement you see in the database world is either for a new relational system or for a new relational front end to one of the older systems. I'm going to look at that phenomenon in a bit more detail later on. So the purpose of the talk is to try and review where we are today, to have a look at how we got to where we are, and then most interesting, I think, perhaps have a look at where we might go next. The other preliminary thing I want to say is that really I have far too much material here. I actually have enough to talk for at least a day on this topic, and therefore, of course, I'm going to have to skimp on some of these things. Of the 5 headings that John just quoted to you, these are the 5. I'm going to skip the first one entirely. I don't want to talk about the 3 generations. I want to jump right into the basic relational model. There I want to talk about what the relational model is and why it is what it is. That will lead me into a brief look at some current relational systems. That in turn will lead to a question, what does it really mean for a system to be relational? And then the last, and I hope the longest part of the talk, will be topics for investigation. In other words, possible future developments. So let me jump into the second area of the talk, the relational model, the basic relational model. What is it and why is it that? Perhaps let me start by asking you a question. How many people here would claim that they already know what the relational model is? Can I just see a show of hands? About 50%. Okay, good. You don't have to know what it is for this talk, but it helps. I'm going to tell you what it is. Briefly, the relational model is a set of concepts, an abstract set of concepts, which are suitable as the basis for building database management systems. The relational model was first defined by a guy called Ted Codd, C-O-D-D, who is in the IBM San Jose Research Center in California. And the next couple of foils that I'm going to show you are actually stolen from a presentation that Ted gives. This is his justification for what for what he was trying to do in that original work. He started work on this in 1968 and actually defined the model in about 69-70. It was first published widely in 1970. So this is Ted talking. If you look around at the systems at that time, they were generally very hard to understand. And those systems that are still alive from that time, that is true, they are still hard to understand. The basic problem seems to be that there are no broad, simple principles underlying the design of those systems. Instead, there's just a whole mass of special cases. The user does not have in his brain a simple conceptual picture of what's going on. He cannot predict with confidence what will happen in a given situation if he hasn't tried it before. He cannot extrapolate from what he knows to what he doesn't know. That's the basic problem. As a result, the training courses are longer, the manuals are thicker, and so on and so on. Another point is that the logical and physical levels of the system were not clearly separated. Now, we always talked about separating logical and physical, but we did not achieve it as much as we would have liked to have done. That led to other problems, as we'll see. The insert, update, delete rules are very, very complicated. For example, anyone here who knows IMS will know that that is true. The insert, update, delete rules there take pages and pages and pages of the manual to explain, and they're very, very confusing. As a result of all of that, installing the system was a very slow job, and it took very highly specialized skills to do it. And when I say slow, I'm talking about periods of 1 year, 18 months, 2 years for complicated databases. Next, because the logical and physical levels were not clearly separated, far too much application programmer effort was devoted to maintaining programs. That is, when a change was made in the physical structure of the database, which you had to do from time to time for example, performance reasons or new requirements coming along, then typically you'd have to go back and change some of the application programs as well because they were tied to that physical structure. And that is still true today in some systems. A figure of 50% of application programmer effort in some installations is quite realistic. And that means that those people are changing old applications instead of building new ones. That's the famous application backlog problem. And the last point, rather separate from all of the rest, there didn't seem to be any good principles for database design. How do you put data elements together into records? How do you put records together into files? Now, this is still Ted talking. The diagnosis, Ted's diagnosis of the problem, the culprit is these spaghetti-style data structures. These data structures are very tangled together, and programmers were forced to navigate, that's the term that is used, navigate around and through those physical structures to get to the data they wanted. Or another way of saying the same thing, really, there was no real data independence. The programmers had to know the physical level as well as the logical level. And then a separate point, which I'll come back to a little later in the talk, there was no simple addressing scheme at the logical level. As a result of all of that, as I said before, very specialized skills were needed to design the database in the first place, to get the data into it, and to retrieve data out of it. Furthermore, there was no support in those early systems, no direct support for end user access, for the real users to get to the data. You had to go through the programmers. I mean, take, for example, the specifications of the Codicil database task group. Those of you who know what they are. Those are the foundation of systems like IDMS, for example. Those specifications were clearly for a programming system. They said as much. They always assumed that you could simply add on end user query front ends later. It turns out that is a very hard thing to do technically. In fact, I would go so far as to say it's impossible to do it 100%. But the contrast in the relational thing, if I jump ahead a few minutes, in the relational approach, the original intent was precisely to let end users get to the data. So here's the database here. Here are the real end users up here. If we could give those end users very powerful operations, things like join and so on, which I'll talk about later, then those users can get directly at the database without having to go through the DP department bottleneck. That was the original idea. Later on, we said, fine, if we have these powerful joins and so on for end users, we can give those operators to programmers too, and programmers can be more productive as well. And that's true, they can. But it was definitely that way around. End users were the primary target, then the application programmers. And finally, this is the third of Ted's foils. Okay, this is Ted's approach to the problem. Clearly what we need is some simple, clean, clear, crisp, precise, well-defined, etc., objects that can be the building blocks for databases. And then we need some simple, clean, clear, etc., operators to manipulate those objects. That's what we need. And an obvious question, at least it's obvious if you're a mathematician, and Ted is a mathematician, an obvious question is, can mathematics help? Now, if you look at mathematics, probably the first thing you would notice that might be helpful here is binary relations. Binary relations are things connected to things. And all of database seems to be about things connected to things. So that's an immediate match there. Furthermore, in mathematics, if you have a problem which concerns n-ary relations, now n-ary relations are things connected to things, connected to things, connected to things, what you do is you break it down into an equivalent but simpler problem involving just binaries. Binaries are a canonical form. So binaries are attractive. But, and this was Ted's real contribution, Ted said, if we could define operators, like join, which work directly on n-ary relations, then two things would happen. The first thing would be that now you could process more information in one operation. Bigger chunks of information could be manipulated in single programming statements, if you like. So people could be more productive. Secondly, the structure that you give users to see, the objects that people look at, these n-ary relations, are very familiar to them because things connected to things, connected to things, connected to things is just like records of fields. and a set of records. In that example, 4 things. There would be 4 fields in the record. A set of records like that makes up a table or a relation. A relation, an n-ary relation, is just a table where the rows are like records. So what Ted did was he defined a set of operators that would process information in that form. Those operators form what is now called the n-ary relational algebra. So that's the background. That was the motivation. I'm now going to take a couple of minutes to explain what the model is. Before I do, let me reinforce something that John said in the introduction. Please interrupt any time if you have comments or questions or you don't understand or criticisms or you want to heckle. It's always more interesting if it's two-way, and I will promise to repeat every question that is asked so that it goes on the tape. Let's then look at what the basic relational model is. It consists of 3 parts. The structural part, which is the objects, those clean, crisp objects, etc., and the manipulative part, which is the algebra, the operators for processing the objects, and then there is an integrity part. I have an overlay here to illustrate this. Here is one of the, there are only 3 databases in the world, you probably know that. One of them is departments and employees, which is this one. One is suppliers and parts, which you're going to see later. And the other one is courses and students. My contribution to this field is that I invented the courses and students database. Okay, the structural part, which is the objects, is basically relations, and relations are just tables. In this database, there are 2 tables or 2 relations. One called dept, which is departments, and each department has a department number, a location, and a budget. And one called emp, which represents employees, and each employee has an employee number, a name, a department number, and a salary. So one row in the department table represents one department. One row in the emp table represents one employee. For reasons that need not concern us now, the columns of the table, which are like fields in the records, are called attributes in the formal relational theory, but I'm not going to bother with that this morning. Basically, tables with columns or tables with fields. Now, there are 2 very important things about these tables. The first one is they have primary keys. A primary key is just a unique identifier, basically. So the primary key for dept is department number. Every department record or row has a unique department number. The primary key for employee is the emp number. Every employee has a unique employee number. That's a very familiar notion. The second part, which perhaps is less familiar, is foreign keys. A foreign key is a field in one table whose values match the values of the primary key in another table. I'll say that again. A foreign key is a field in one table whose values match the values of the primary key in another table. For example, in the employee table, there's a field department number, and that is a foreign key. Every value of department number in this column here should also appear in the column there, which is the primary key of dept. For example, if you have a record saying that Joe is in department 7, you better have a department 7 up there. Because if you don't, the database is not in a state of integrity. So that's what a foreign key is. So the structural part is basically tables with primary and foreign keys. The foreign keys are very important. They serve to connect the tables together in a sense. The other portion of the structural part is domains. I don't have time to discuss domains in detail. I'll just tell you briefly that a domain is a conceptual pool of values. For example, in this department and employee database, there is a pool of department numbers, a conceptual set. And every value appearing in the department number column in this table, and every value appearing in the department number column in this table, all of those values are values from that conceptual pool. But for the purposes of this presentation, we can more or less forget about domains. They're important, but they're not as important as tables. I have a foreign visitor. It's a bug. Go away. The manipulative part is the algebra, and I'm going to jump over that. I'll come back to it in a second. The integrity part consists of 2 general integrity rules. General in the sense that every database that conforms to the relational model must obey these two rules. Now, any given database will have its own specific rules as well. For example, the department employee database would have a rule that says, let's say, salaries must be positive. But that is local and specific to that database. These general rules apply to all databases. They have very grand names: entity integrity and referential integrity. Entity integrity just says primary keys must not be null. Null is a value meaning information missing. So what that rule is basically saying is you cannot have an employee in the database where you don't know the employee number. You cannot have a department where you don't know the department number. Again, I'm giving you a subset of a much longer talk. I could justify that rule, but it would take me several minutes to do so. For the purposes of this presentation, just please believe primary keys must not be null. The second rule, referential integrity, has to do with foreign keys. Let's see, a foreign key is a reference from one table to another. And what the foreign key rule says is when you have a reference, the thing that you reference better be there. In other words, any foreign key value must match an existing value of the corresponding primary key. If you have department 7 here, you better have department 7 there. Unless the foreign key is null. Now, it might be possible under some circumstances for foreign keys to be null. For example, if it is possible in this company for an employee to be in no department at all at a certain time, and that's possible in IBM because it happened to me. So don't inquire too closely. My personnel record then in the personnel file would have a null department number. So the rule for foreign keys is either they are null, if that's allowed, or if they're not null, the value must match a value of the primary key. So that's the model. We haven't looked at the algebra yet, but let me just stress one thing at this point. The relational model is not just structure. You will see many, many people in print talking about data models and the relational model in particular as if it was just tables. It is not just tables. It is tables plus at least operators. You see, if you just have structure but you don't have any operators, you can't do anything with the structure and it's not interesting. But if you compare two systems, it's not enough to compare the data structures, you must compare the operators too. So the operators and the integrity part are integral parts of the model. Let's look at the manipulative part briefly. The manipulative part is the algebra. The algebra consists of operations on relations or tables. And just like, let's see, for example, set algebra is operations on sets, and matrix algebra is operations on matrices. Relational algebra is operations on relations. Each operation takes either one or two relations as its input and produces another relation as its output. For example, select. Select picks out rows of a table. So it takes one table in, it picks out some of the rows, and those rows, of course, are a sub-table, and a sub-table is another table. So the output is another table. For example, you might say select all employee records where the department number is 7, and you get just those rows. So select picks out rows, project picks out columns. You might say project the employee table over the employee number and salary columns. You get just those two columns, and those two columns are a sub-table, which is another table. Product takes two tables and produces a table which is all possible combinations of the input. So if I have a table with A, B, and C, these are whole rows now, row A, row B, row C, another one with X and Y, I will get the concatenation AX, AY, BX, BY, CX, CY, all combinations. The next three are probably familiar to you. They're just the standard mathematical operations: union, intersection, difference. Union of two tables is a table which has a row for every row in the first table or in the second table or in both. Intersection is the rows that are in both. Difference is the rows that are in the first and not the second. And the last two, which are the most complicated, but they're still not very complicated. First, join. Join takes two tables which have a common column. For example, these two tables both have a column of B's. And you can join the tables together on that common column on the basis of matching values in the common column. For example, A1, B1 joins to B1, C1, gives us A1, B1, C1. A2, B1 joins to B1, C1, A2, B1, C1. A3, B2 joins to B2, C2, A3, B2, C2. And notice there is a B3 in the second table, but not in the first. So there's no B3 in the result. That's the way join works. Any row that has no match in the other just does not appear in the result of the join. And you see, because the result of the join, like everything else, is another table, you can go on and do selects and projects and products and so on it. Finally, divide. Divide is the most complicated of these operators. Unfortunately, it's the one you need least. I'm just going to explain it in its simplest possible form. In its simplest possible form, divide takes two tables, one which has two columns, that is the dividend, and one which has one column, that is the divisor, and it produces a result, which I guess is the quotient, which has one column. And this is the way it works. You get in the result all of the values in the first column that match in the second column all of the values in the divisor. I'll say that again. You get all of the values out of the first column that match in the second column all of the values in the divisor. You see, the divisor is x and z. A matches x and A matches z. A also matches y, but that's irrelevant. So A appears in the result. B matches x but not z, so we don't get B. And C does not match either x or z, so we don't get C. Now those are the 8 operators of the algebra. If you've never seen them before, of course I do not expect you to remember them now. What is important for now is to understand that operators like this exist and can be defined and can be used. And these operators are very high-level operators because they allow the user to process whole tables in single operations. Incidentally, although Ted defined these 8 operations originally, you don't actually need all of them. 5 of them are primitive, and the other 3 can be defined in terms of the first 5. The 5 that are primitive are select, project, product, union, and difference. Intersection, join, and divide can be defined in terms of those first 5. Nevertheless, join in particular is such a useful operation in practice that systems ought to support it directly, even though it is not a primitive operation. Yes?
Why isn't difference shaded at the bottom?
The question is, why isn't difference shaded at the bottom? The difference between two tables A and B is all of the A's that do not appear in B. So the difference of B and A is all of the B's that don't appear in A. It's a directed operation, like subtraction in ordinary arithmetic. That brings me to the end of the first part of what I want to tell you about and leads me into the next topic, current systems. I'm going to show you a list of some current products. All of the products in this list at least claim to be relational. I do not think they all are relational, and I'll explain that point in a few minutes. But the point is, the market perceives that relational is a good thing to be. And by the way, this is products. It does not include prototypes. These are all things you can go and pay good money for. And furthermore, it is very incomplete. Since this list was compiled, I could add 4 or 5 times as many as I'm going to show you. But I think conservatively that there are at least 40 real relational systems now. That 40 includes a lot of systems for micros. If you were building a database system for a micro, you'd be insane if you didn't build a relational one, frankly. My list takes up 2 pages. The first one, Datacom, is a system that has been around for many years, but in the last few years it has started describing itself as relational. I'm not going to describe all of these systems, just point to a few. Oh, IDM, that's an interesting one. IDM stands for the Intelligent Database Machine. It's a database machine. Again, if you were building a database machine, you would almost certainly make it a relational machine. There's all kinds of reasons why that is true. That was produced by a company in California called Britton Lee. I believe they've sold something like 250 or 300 of them by now. Originally they announced a 500, then a smaller version called the 200, and this is a back-end machine which attaches to a front-end host. The back-end machine is a specialized processor which runs a conventional software database management system, and the software database management system is relational. It's very like Ingress, as a matter of fact. And the idea is that this machine would be marketed to OEM buyers who would provide the software and the host to interface to the user. So in the host, you have software which talks to the terminal, does the reporting and the formatting and that kind of thing, and that software passes the database requests down to the IDM. More recently, Brittany announced the 600 and a 300. Now the 600 is a 500 plus a VAX, so they're providing the front end as well now with the front end software. And the 300 is a 200 plus a VAX. And then a few months ago, they announced something else. I've seen the announcement for this, but I don't know whether it ever materialized. It sounds very attractive. It was called the Shared Database System, and it's an IBM back-end machine, a 200 actually, with up to 64 IBM personal computers on the front end running the SQL language. I'm going to say more about the SQL language in a few minutes. That looks like a very attractive system to me, but I don't know what has happened to it. I saw the announcement, that's all. Maybe someone here can tell me afterwards. The red and black is just a differentiation. The question was, what was the significance of the red versus the black? It was just to separate the lines, no magic. Ingress is another interesting one. Ingress was originally built at the University of California in Berkeley. And more recently, the people who did it formed a company called Relational Technology to market the system. The original version ran on VAX. More recently, they have announced a version called Micro Ingress, which runs on the 68,000 chip. And that's a trend I think we're going to see more of over the next few years, the larger system migrating down to smaller machines. In fact, jumping to my next page, another system here, Oracle, has done the same thing. Oracle is another system that supports this SQL language. And what is impressive about Oracle is the number of different systems that it runs on. Originally, it ran on PDP-11s and VAXs, then on the Data General Eclipse. It runs on IBM 370s and 370 lookalikes under VM. They have announced an MVS version. I don't know if it's been released yet. They also have a version that runs on the 68,000 chip. And they originally designed their system to be very, very portable. They say that it consists of about 2,000 modules written in the C programming language. And if you don't know what the C programming language is, it is outgrowth from an earlier language that was called B. That's all you need to know about. See, it was designed to be portable. Of those 2,000 modules, they claim that you only need to change 30 of them to move from one system to another. That comes from a company which was originally called Relational Software. Relational Software and Relational Technology are both in the San Francisco Bay Area, about 20 miles apart. And what happened was they kept getting each other's phone calls, which is very, I mean, can you imagine how annoying that would be? You're selling Oracle and you get bright calls saying how much is Ingress, you know. So they recently changed their name to Oracle Corporation. And last on the list here, IBM, a couple of years ago announced a system called SQL DS, which ran on DOS, and then more recently, Release 2 runs on VM as well, and this year they announced a product called DB2, which runs on MVS. So IBM now has a range of relational systems, mainline strategic products running on all of the mainline operating systems. And these systems, by the way, also support the SQL language. SQL was a language that was first implemented in the form of a prototype from IBM called System R. And what happened was that IBM's competition perceived that IBM was going to be endorsing this language in the form of products before IBM actually did. And they started jumping on the SQL bandwagon. Oracle, I think, was the first one to produce a SQL system, but now there are something like 12 products out there that all support some dialect of SQL, not counting the IBM systems. In addition to that, in the States, the American National Standards Institute has a database committee which has the charter of producing a relational database standard, and they took as their initial working document the IBM SQL definition. So like it or not, SQL is going to become a very important language. It might become an actual standard, and it almost certainly will become a de facto standard. In fact, I often describe SQL as the COBOL of relational database, and that is meant both in good senses and bad.
So my question, what does the IBM PC got in terms of relational?
The question is, what does the IBM PC have in the shape of database systems? It's my understanding that there is not yet any product from IBM that is a database manager on the PC, but there are many products from software houses that run, and most of them are relational. For example, there's one called DBase 2, which runs on the PC. I think MicroRim runs on the PC. The Condor system, I think, runs on the PC. There are several. I'd have to go and look at my notes to give you a definitive. It's impossible to keep up anyway. Every time you open Byte magazine, there's a new ad for a new system. Now, this leads me right into my next topic. What is a relational system? Because all of those systems say they're relational, and yet they're not all equivalent in function. There are big, big differences. So what I'm going to do is give you a proposed definition for relational systems. You see, that relational model that I described a little while ago, which you can view as a prescription for building a database system, that prescription consists of a number of line items. Depending how you count, there are 5, 10, 15, 20, 30 line items in the list. And not all of those 30 are equally important. Now, some of them are crucial. You've got to have tables, of course. But other things are, well, maybe nice to have, but not so important. For example, the divide operation. It's nice if you have it, but even if you don't, there's still a lot of useful things you can do. So the question is, what is the minimum subset of the total model that a system ought to support to genuinely claim itself as relational? In the States, there's a law called truth in labeling, which means that if you go into a supermarket and you buy a can of frozen peas or something, and it says contains 0.07% monosodium glutamate, it better contain 0.07% of monosodium glutamate. Truth in labeling. We need truth in labeling in database systems. There is a lot of confusion here. I'm going to show you something that I took from a journal called Information Systems News. About a year and a half ago, they produced a special issue on database systems. In the middle of the pull-out supplement, they had a big table listing all of the available products for large and medium-sized machines. And this table, of course it was a table, I really am bigoted. This table had the name of the product, the name of the vendor, the price, the software, operating system requirements, the hardware requirements, and so on. And one of the columns in the table was architecture type. And the entries here were things like hierarchical, codicil, and so on. Here are some of the entries in that architecture type list. First, inverted list relational like. Now that confuses me right away, because inverted list is a physical structure and relational is a logical structure. When we talk about relational databases, we mean the user sees tables and the user manipulates tables at the logical level. Down at the physical level, you can do whatever the system is smart enough to do. But those are two different things. Relational like appeared many times. Relational shared structures, I have no idea what that means. Network with relational view. Hierarchical with relational capabilities. Quasi-relational, I really like that. And you can see what happened, okay? Here's the guy compiling the table. He gets on the phone to the vendor and says, well, how would you describe your system? Well, it's sort of quasi-relational. No deep understanding. And then there were some that really were relational. Well, Ted Codd and I were talking about this. We were very concerned because, we had started out with something that was very cleanly defined, and here was the world fuzzing it up. So we wanted to try and get back to the clean situation. And we came up with this proposal. And Ted documented this in the Turing paper in 1981. I don't know if you know, but Ted received the ACM Turing Award for his relational work. And the Turing Award is really the #1 award in computer science. People who've had it before have been people like Dijkstra, Tony Hoare, John Backus, and so on. And I was very pleased that Ted got this. In this paper, he has this proposal. To qualify as relational, a database management system must support tables and nothing but tables. It's important to say what is not there as well as what is there, because otherwise a system like IMS, for example, could say it was tables and therefore relational. Because the segments in IMS, which are like records, are like the rows in tables. So tables and nothing else at the logical level. Specifically, there are no user-visible navigation links between those tables. And then, out of those 8 operators of the relational algebra, at least select, project, and join. Select, if you remember, picks out rows, project picks out columns, and join glues 2 tables together. And when I say support, select, project, and join, I mean, let's take join specifically. The user should be able to join any table to any table, wherever that makes sense. The user should not be constrained to only being able to join tables where there is some physical connection under the covers. Now, there are systems on the market today that support join, or say they support join, but the join only works if the database administrator has thought 6 months ago, I expect people want to join these 2 tables together, I better physically connect them through some kind of index or pointer chain or something. If that's the situation you have, you're back in the bad old game of having programs dependent on the physical structure. If you need to change the physical structure, you have to change programs, and that's what we wanted to get away from. So these operators should be supported without requiring physical predefinition of access paths. Question?
Isn't it true that to join different areas, you have to have a common key between them anyway, so that 6 months before you have to allow for that key in the areas regardless?
The question is, isn't it true that to join 2 tables, you would have to have a common key in the 2 tables to do the join on, so you therefore had to think about at least that 6 months ago. You do have to have a common field. It doesn't have to be a key, by the way. It can be any field. But you do have to have a common field, but the argument is fields are part of the logical structure of the data. You thought about that when you did the logical database design, and you separated the logical structure from the physical structure. Now, there are systems on the market today that support tables but do not support select, project, and join. They only support operators like get me the first row, get me the next row, get me the next row. We propose that those be called only tabular. And then there are systems that support select, project, and join but require physical predefinition of access paths. We don't like those either. And then there are systems that do what we say. Now, the reason we have this definition is very pragmatic. First of all, it is these high-level operators, the relational algebra operators, that make people productive. If you only have tables but you don't have the high-level operators, you don't have the productivity which you can get from relational systems. So that's the first point. Second point is, select, project, and join are not the whole algebra, that's true, but they're the pieces of the algebra you need most of the time. I would guess 95% of all things you want to do that you can do with the algebra, you can actually do with just select, project, and join. So that's the big, useful subset. And third point, to implement a system like this that supports select, project, and join without requiring predefinition of access paths, that's difficult. That's a hard thing to implement. You are really requiring the system to have an optimizer that takes what the user says and figures out the best way of implementing it. Because if the system just does precisely what the user says, it probably will not perform very well. So by insisting that these operations be supported and the system be a realistic system, we're really trying to separate the sheep from the goats. And as a matter of fact, you can draw a whole spectrum of relational systems now. This circle down here represents the relational model. I is the integrity part, the 2 integrity rules. M is the manipulative part, the algebra. And S is the structural part. They're interesting initials, aren't they, as you go around? Well, a system that supports only tables and not the algebra, we'll call that tabular or semi-relational, and it is not relational. This is a very sharp dividing line here. A system that supports tables and select, project, and join is relational, minimally so. A system that supports tables and the whole algebra, for historical reasons, is called relationally complete. It's not a very good term, but never mind. And then a system that supports everything, including the two integrity rules, we would say that is fully relational. Now, I will tell you, as far as I know, there is no product today that is fully relational. There are some that are getting close, and I expect to see some very soon, like within a year or two. There are many systems that are relationally complete. For example, Ingress is, Oracle is, the IDM is, the IBM systems, DB2 and SQL-ES, those are. There are systems that are minimally relational. For example, DBase 2, I mentioned that micro system, fits in there. So that's the proposal. You can take it or leave it, you know. There's nothing sort of religious about this. And by the way, I don't want you to get the idea that I am hung up on the term relational. See, fundamentally, it is not important whether a system is relational or not. What is important is, what does the system do? What function do you get? That's obvious. All Ted and I were trying to do with this was say, here is a list of functions which any decent, self-respecting, modern database management system ought to provide. If we can agree amongst ourselves that the word relational means that list, then we can stop arguing at this level and move on to more interesting things. So this provides a basis for comparison of different systems too. Okay, that was the point. Yes?
Sorry, I missed it. What's the difference between minimal relational?
The question was, what is the difference between minimally relational and relational? And the difference between these two, minimally relational, it supports select, project, and join. Relationally complete, it supports all of the algebraic operators, including, for example, union, divide, and so on. So there are some systems that only support select, project, and join. And so there are some things you can't do with those systems. Is that the clip that means I have to stop? Can I carry on?
Yes, you're right.
I'm on. While we're on this question of relational systems, I want to take 2 minutes to say something about performance. Something that you... Start again. There is a myth that has been going around the commercial world and the database world for several years now, which is expressed in various forms. One is, oh yeah, relational is okay for query, but it's no good for real work. Operational databases or production data or transaction processing or whatever you want to call that. Another one you hear is, relational systems require a hardware breakthrough, that is, hardware associative memory, if they're ever going to perform acceptably, and so on and so on. Well, I think you can guess my opinion on that. But I'm going to skip over the file that says what it is. This is my position statement. I believe there is no intrinsic reason why a relational system should perform any worse than any other kind of system, or indeed any better. Come back to that point in a minute. Let me try and justify that position. This is another of those areas which, to do it justice, it should take at least sort of 30 or 40 minutes, and I only have 2 or 3, so I'm going to go very quickly over this. But fundamentally, what is important as far as performance goes is not what the database looks like to the user, but what the database is physically like. It is the physical structure that dictates the performance of the system. So basically, you have to ask 2 questions. Is this relational system such that it provides the right kind of physical structures on the physical disk? Well, let's look at that question first. In most relational systems today, the physical structure is basically inverted lists, B-tree type indexes. There are some systems that give you hashes and things as well, but every system I know gives you at least indexes. Now, indexes do perform perfectly well in many, many cases. There are many applications where indexes are fine. In fact, if you have to choose one physical structure, there's no question you would choose indexes. Now that must be true, because if it was not true, nobody would use VSAM, and VSAM is precisely an indexing structure. So for question 1, if you have an application where indexing is the right structure, you're in good shape. If you have an application where you really need, let's say, hashing to get the performance you want, then most systems today will not give you the performance you want today. They might in a later release when we add hashing, but today they won't. In question 2, assuming the answer to question 1 is yes, you do have the right structures, then is the system smart enough to take high-level relational requests and convert them down into code on those indexes that is as good as hand code, as good as a clever programmer would write coming directly in at that level? Well, I'm going to quote the IBM systems here because they're the ones I know best. SQL DS, and indeed DB2 also, they take SQL statements as the user requests and they compile them. By the way, that's important too. They compile them, not interpret them. And they produce code down on the indexing level that in many cases is as good as hand code. That in fact is exactly what the optimizer is for. I mentioned the optimizer component you had to have. These systems have an optimizer, and this is exactly what they do. They try and generate code as good as hand code. Now, in many cases, they do it. There are also some cases where they don't. I'll give you a trivial example of that. In the SQL language, you can ask a question like, select all the information you have about employees where the employee number is in, and then you list some employee numbers, 1, 5, and 93. So you're trying to find information about those 3 employees. Now, probably the best way of implementing that is to use the employee number index, which is almost certainly there, and go directly to employee 1, directly to employee 5, directly to employee 93, and that's it. But what the optimizer does with that query today, as soon as it sees that in condition, it says, oh my God, this is complicated, and does a sequential scan. But the point is that we know that that's a case where we don't do a very good job, and we can fix it. And we can fix it transparently without affecting the user level at all. That's what this data independence is all about. So that, you see, this optimizing technology is in its infancy. We're just starting. When I said a moment ago that there's no reason why relational systems should perform worse than other systems or better, actually, in a sense, they might perform better eventually, because the whole point is they are optimizing systems. See, suppose you look at a record level system, an IMS system or an IDMS or Adabas or something, and suppose you're writing record level statements to compute a join. So the program is joining A and B. Now, sometimes you need to do that even if you don't have join operations. Now, if you're joining tables A and B, there's fundamentally 2 things you can do. You can go through the A's and for each A find all the B's, or you can go through the B's and for each B find all the A's. Now, depending on the physical clustering of the data on the disk, depending on data distributions, depending on the relative sizes of tables A and B, and many other factors, one of those 2 approaches will outperform the other by orders of magnitude. Now, if the application programmer at the record level chooses the wrong approach, there is no way you can optimize it. In a SQL-like system, you say, join A and B. And the optimizer does the right thing because it knows this information. And furthermore, the right solution today may not be the right solution a year from now, because the disk may change. You may change the physical clustering. So you need to re-optimize. Re-optimizing in a relational system is trivial. You just recompile the statement. And the optimizer now does the other right thing. Re-optimizing the hand code is very hard. You've got to rewrite the program. And perhaps you don't. So there is a sense in which relational systems might ultimately perform better than non-relational ones, because the optimizer can have information available to it that is not available to the hand coder. So I conclude from that there is absolutely no reason why a relational system that is implemented on perfectly conventional hardware using perfectly conventional software techniques should not perform completely acceptably. Torture sentence, but you get the point. And exotic hardware, hardware associative memory and so on, is not required. As a matter of fact, I don't even think it would help very much in most cases, but I don't have time to discuss that. But please understand, this is a very arm-waving argument. I am not saying that a relational system today is going to perform like IMS today. If you have one particular application where you know precisely the kinds of transactions you want to run, there's no question that you can build physical structures and tune the system in IMS or something like that today, and you will get better performance than a relational system today. But I repeat, that is not an inherent situation, and I think in a few years the relational people will catch up. After all, you're comparing release 1 or 2 of a new technology with a system that's been out there for 15 or 20 years and has been tuned for those 15 or 20 years.
The other side, when you're talking about performance, you're really only talking about machine performance, not the overall performance of the DVD shop.
That's a very good comment. The question is it fair to say that when I'm talking here about performance, I'm only talking about machine performance, not the overall performance of the DP shop? Of course. I'm talking about machine performance because it's always been regarded as the Achilles heel of relational systems. But if you look at the total installation performance and the people performance, well, I'll tell you, the first IBM customers on the SQL systems have come back and told us they're getting anywhere from 5 to 20 times improved productivity with the systems. And that was the point. The argument is that machines are getting cheaper, people are getting more expensive. So that, the economics of the 80s says we want to optimize people performance rather than machine performance. My point here is that we could optimize machine performance too in a few years' time. And that brings me to the last section of the talk, topics for investigation. I have a very large number of possible things that I could talk about here also, and I'm just going to hit some highlights. Somewhat arbitrarily, I've divided these topics up into user interface topics, in other words, things that the end users and programmers will see, system implementation topics, tools and aids, and miscellaneous. I told you the suppliers and parts database was coming. Here it is. I'm going to use this for a couple of examples. This database is 3 tables. A supplier table called S with supplier number, name, status, and city. Supplier number is the primary key. A parts table with part number, name, color, weight, city. That's the city the parts are stored. Part number is the primary key. And a shipment table called SP. And a row in here says, for example, that supplier S1 is shipping part P1 in a quantity of 300, let's say. And in this very, very simple database, I assume that there cannot be 2 shipments of the same supplier and same part at the same time, so that for any given shipment, the combination supplier number and part number is unique, so the primary key is the combination supplier number and part number. There are also 2 foreign keys here. Supplier number in the shipment table is a foreign key matching supplier number in the S table. And if you have supplier 1 here, you better have supplier 1 up there. Likewise, part number here is a foreign key matching part number there. If you have part 10, you better have part 10. Maybe. Okay, out of my long list of user interface topics, the first one I want to mention is primary keys. Now, you remember the primary key is that unique identifier thing. As a matter of fact, it is unique, and also nulls are not allowed by integrity rule number 1. Primary keys are crucial in the relational model because they are the only thing in the model that provide a system-guaranteed addressing mechanism. That is to say, the only way you can pinpoint one specific record is to say it's in this relation and its primary key is that. It's a supplier record and the supplier number is S3, and that will pinpoint one particular record. That is the only way you can pinpoint one record. That does not mean that users can only address records by primary key. Users can address records any way they like. They can say, give me all the suppliers in Sydney or something like that. But they don't know how many records they're going to get back. The only way to be guaranteed to get one is to talk in terms of primary keys. Now, the situation in systems today is that most systems do not support primary keys. For example, in, again, the IBM systems, what you have is you have the ability to force a field to be unique, and you have the ability to force a field not to be null, so you can impose that discipline for yourself, but the system doesn't know what you've done. And it turns out there are many places where it needs to know what you've done. I will illustrate that in a moment. For now, just accept that sometimes the system needs to know about that. So what I expect to see in future systems, and this is the way you create new tables in SQL, you say create table, S is the name of the table, the columns are S number, S name, status, city, you specify their data types like character string, decimal or whatever. I expect to see a new clause, primary key, and then you name the primary key. And the system understands that, and it enforces the uniqueness without me having to say so, and it enforces the not nullness. The second thing that I want to see just as soon as possible is support for foreign keys. You remember foreign keys are those fields in one table that match the primary key of another table. For example, in the suppliers and parts database, the supplier number in the SP table is a foreign key which identifies a supplier number in the S table. Now, there's more to foreign keys than that. It is not enough just to say this field matches that one. You also have to consider what happens if somebody tries to violate that rule, that constraint. In fact, for each foreign key in the database, somebody, the database designer actually, has to say, are nulls allowed for this foreign key? Take the shipments. Does it make sense in this enterprise that I am representing in the, in the database? Does it make sense for a shipment to exist where you don't know what the supplier is? Well, probably not. Probably the rule for that foreign key would be nulls not allowed. But if I go back for a second to the employee department one, remember employees, if they are allowed to be in no department at all, can have null foreign keys, null department numbers, so the rule there would be that nulls are allowed. So the database designer is trying to capture the policy of the enterprise by answering that question. Has to do that for each foreign key. Second, what if somebody tries to delete the target of a foreign key reference? If you delete supplier 1, what happens to the shipments for supplier 1? Well, in general, there are three possibilities. One is that you delete the shipments too. The delete cascades to those shipments. That's what happens in hierarchies today, as for example in IMS. A second possibility is to disallow the delete if there are some shipments. Restrict the delete to the case where there are no matching shipments. And the third possibility is to delete the supplier and set the references to that supplier to null. Of course, that only makes sense if nulls are allowed in the first place. And then the third question is, what happens if somebody changes a supplier number? Suppose you change the supplier number of S1 to S20. What about the shipments for supplier 1? Well, in general, you have the same three possibilities. Cascade the change and change it in the shipments too. Restrict the change to the case where there are no matching shipments, or set the references to null. Now, again, if you haven't seen this before, I obviously don't expect you to remember the details, but the point is that this foreign key stuff is absolutely crucial to the integrity of the database. And as a matter of fact, when I said a minute ago that primary keys are important, they are important, but the number one reason you need support for primary keys is so you can support foreign keys. A system that supports primary keys without foreign keys is no big deal. What I really want to see is support for foreign keys. And I will admit, frankly, that the biggest deficiency in relational systems today is lack of support for foreign keys. Because you see, if the system will not maintain this integrity for you, who gets to do it? Answer, the user. That means you have to write procedural code to do this stuff yourself. I just hate to think of every installation for every database, for every foreign key in the database, writing a bunch of code to do this stuff, when really the system should do it. And as a matter of fact, some systems are beginning to do this, but nobody, as far as I know, does a 100% job, and I would like to see that as soon as possible. Question?
You also pointed to Achilles heel in the
question is, isn't this the Achilles heel of the Achilles heel in terms of performance? I really don't buy that argument at all. If you're concerned about integrity, you have to do this stuff. Whether the system does it or the user does it, the performance is pretty much the same. Actually, the system could do it slightly more efficiently than the user, but performance I don't think is a significant factor. If this is a requirement, if you require your database to be in a state of integrity, you have to do it. And performance is a non-issue as far as I'm concerned. It is not performance that this is the reason that this is not implemented. I don't have time to discuss why it is not implemented. So here what I expect to see is it more extensions to the create table. This is create table for the SP table. Here are the columns. Primary key is the supply number, part number combination. And there's a foreign key, supplier number, which identifies a supplier. And nulls are not allowed. And delete of supply is restricted. An update of supply number in the S table cascades, or whatever the rules are. And then again, part number is another foreign key, etc., etc.
Adding fields as a foreign key would require alteration of the program.
Offline. I only repeat questions I answer. That's not fair. The question is, adding a field, if you add a field that is a foreign key, does that mean you have to change programs? And that unfortunately requires a lot of discussion, and I simply don't have time. I'm sorry. But I'll talk to you in the break, if you like. Third one is a different kind of thing, outer join. I'm going to take a different database. This database has some courses, C1 and C2, and courses have offerings or classes. And course 1 has an offering 01, and course 1 also has an offering 02. Course 2 has no offerings right now. Now, if you join those two together over course number, C1 joins to C1, and you get C1 Algebra 01 MIT. C1 joins to C1 again, you get C1 Algebra 02 UCLA. C2 has no offerings, so C2 does not appear in the result of the join. That's the way the join works, as I told you before. In a sense, you can say that that join has lost information. That's not a very accurate characterization, but in a sense. That can be very annoying. Now, if you're trying to produce a report out of the database which says, list all of the courses, and for each course list all of its offerings, well, in that report, you'd like to see course 2 with no offerings, right? And users are very surprised when it doesn't appear. And I know for a fact that IBM is already being beaten up by its customers because that problem happens. It's a problem users discover for themselves very fast. So what we need is a new kind of join, which is usually called the outer join. And by contrast, the ordinary join is called the inner join. And the outer join is the same as the inner join where things match. So these two rows are the same as that. And then when you have a row which has no match, you preserve that row concatenated with null values in the other positions. So that's preserved information for course 2. The situation today is that there are some vendors that have systems that support some kind of outer join. Nobody supports it in full generality. And the solutions that I have seen in existing products I regard as very kludgy, frankly. Nevertheless, the fact is some systems have them and some do not. IBM does not yet, which is why it's being beaten up. And it's a very important requirement. For example, one company that does have an outer join claims that 80% of all applications need this function. I think that's a bit high myself, but certainly 25 or 30% I think could use this function, and that's quite a high percentage. We need this urgently. The problem with it is this example is very trivial and it's easy to understand, right? But when you really poke into outer join in generality, it turns out to be very subtle. It has all kinds of counterintuitive properties. And that's why it's hard to do the job in full generality. Next, view updating. Maybe you don't know what a view is. A view is a virtual table. Okay, you have a database which has some tables in it, And views are tables that the user sees, but they don't exist in their own right. They're different ways of looking at the tables that are really there. I'll give you a trivial example. If you have the suppliers table as a real table, some user could see just the suppliers located in Sydney, for example, which is actually a subset of the table, and that would be a view. The table isn't really there. It's a way of looking at the real table underneath. Now, if you're going to build a system which has views, you're going to pretend that tables are there that are not really there. You have to allow users to update those tables. And then what you have to do, you're the system, you have to catch those updates and go down to the real data underneath and change the real data underneath to make it all work. So, if the user updates a view, the system has to map the updates to the underlying relations. That means the system has to be able to identify the records that are affected down underneath. That means it has to be able to address them. That means it has to know about primary keys, because that is the only way to address them. So that's another reason why primary keys are important. And as a matter of fact, if the view is not just a subset of one table, but is a join, it has to know about foreign keys as well. Let me show you. If I go back to this picture again, this is nothing to do with outer join now. Forget outer join. Look at this inner join. That could be a view. Now, the user comes along and says, okay, I want to delete this second row here. Now, if you think about it, you can achieve that effect by actually deleting the second row in that table there, because that will leave one row for course 1, join it to here, and you'll get just the one row there. That works. So it is possible to take this delete and map it into a real delete on the real table. But the reason we know that works is because that join was a join over a foreign key here matching a primary key here, and we understood the semantics underlying that primary key foreign key match. And that's how we were able to figure out how to do the delete. And if the system is ever going to figure out the same thing, the system has to know about primary keys and foreign keys as well. So there is another reason why keys are important. The situation today is some systems don't support views at all. Some systems support views, but they're read-only. Some systems support views with update, but the update rules are very ad hoc. For example, in all of the SQL systems I know, the system will actually allow you, it will not allow you to update some views you should be allowed to, and it will allow you to update some you should not be allowed to, precisely because it doesn't know about keys. This key stuff is so important. Yeah.
Doesn't this mean that all fields in a record effectively become keys?
The question is, doesn't this mean that all fields in the record effectively become keys? The answer is no. When I talk about updating joins, the joins you can update are precisely the ones that are primary key to foreign key matches. There are other joins that are inherently not updatable. And I, again, don't have time to expand on that. I apologize. Let me show you one other thing in the user interface stuff. There's a lot of other things I could say. Bill of materials. You know, this is the structure where you have parts that contain lower level parts as components, which contain lower level parts as components, and so on. Now, it is very easy to build a structure for that in relational systems. You have a parts relation, which is the parts list, primary key part number, and another relation that represents the many-to-many relationship between parts and parts. I call it PP, has an assembly number and a component number. For example, part 1 contains part 2. And it takes 10 part 2s to make a part 1. So assembly number and component number are really part numbers, and they're both foreign keys. Now, in relational systems today, or most of them anyway, to write applications against that structure, let's take a particular case, the parts explosion application, where you're given a part number, say part 1, you want to find all of its components to all levels. To write a program to do that is very difficult in relational systems. It can be done, but it's clumsy. The real reason is you start with a part number, you explode it, that put me off. You explode it to one level, and then for each part of that level you explode to another level, then to another level, and so on, and you're going to go down n levels, And for each of those n levels, you're going to hold a position. So you have n position holders. And the problem is you don't know what n is ahead of time. And existing relational systems don't give you any way of dynamically creating new position holders. You can create 1 or 10 or 1,000, but not n. And so either you say, well, I'm never going to go more than 10 levels, and you declare 10 of these things and you explode to 10 levels, and the first time you get to an 11th level, you're in deep trouble. Alternatively, you play all kinds of silly games, juggling things around to reuse the one position holder over and over again. And you can do that, but not a good idea. Clearly what you need to be able to do, well, I'll come to that in a second. Second thing is, and perhaps this is more fundamental, you cannot write a part explosions query at all. For essentially the same reason. Because basically what you need to do is take that table PP and join it to itself, matching component number to assembly number. And you need to do that n times for the n levels. And you don't know what n is. So you physically cannot write the n comparisons. There's no way to write n things if you don't know the value of n. If the language is only relationally complete, if it only supports the relational algebra. So clearly what we need is extensions to the relational algebra to do that. We need recursion in database programs. This is a recursive structure, and obviously the right way to do it is to recurse for each level, and each time you recurse, you create another position holder, and you go down n levels. Of course, if you're in COBOL, well, serves you right. Finally, I didn't say that. Erase that from the tape. Finally, you need a way of saying there are no cycles in the structure. You know, if part 1 contains part 2, and part 2 contains part 3, and part 3 contains part 4, and part 4 contains part 1, the recursion will go for a long time. Let me skip, the clock has rung. Let me skip very quickly to system implementation topics. Further automatic navigation. Automatic navigation is where the system takes a high-level statement, like a SQL statement, and figures out how to navigate through the physical structures on the disk to implement that. And we do quite a good job on indexes today. What we would like to do is slide in hashes, pointer chains, any other access structure you can think of, and navigate through those things as well. And we can, in principle, we can do that in future releases of the products without changing the interface up here because of the separation, the data independence. Further optimization, even in the structures we have, as I indicated, we know there are some cases where we don't do a good job, and we will improve. I expect to see PhD theses coming out of universities over the next several years on new, clever ways to optimize relational expressions, and that stuff can then be folded into products. I think we are today in optimizing relational expressions where the programming languages people were, say, 15 years ago on optimizing arithmetic expressions, and they're very, very good at it now. And I think we will get good in a few years. Specialized hardware, I indicated already, associative disks might help in some applications, although I think they're very specialized. Tools and aids, I have two. Physical design aid and a logical design aid. I have a somewhat unorthodox opinion in this area, I think. I happen to think that a physical design aid is very, very important, but a logical design aid is not. Let me explain. This optimizer, in the optimizing systems like DB2, what it does is it takes the request and it looks around the database to see what indexes there are, and it figures out which indexes to use. Great. Question, where did the indexes come from? Answer, some human being put them there, the database administrator. Question, how does the database administrator know which indexes to put there? Answer, either he guesses, or he has to know how the optimizer works. And neither of those is a good answer. The whole point about optimization is it should be automatic and transparent. It's a black box. It's magic. It just works. What we need badly is some mechanical aid to tell the database administrator where there should be indexes. And in IBM research, such a tool has been built. The input to the tool is the set of queries that you typically want to ask the system with their relative frequencies, and then the design aid goes and talks to the optimizer and says, if you had these indexes, what code would you generate? And it talks to the optimizer and figures out the best mix of indexes and comes back and then tells the database administrator. It is still a human decision as to whether you want the indexes, but that's how it works. What is interesting about this is that this is a problem that is only going to get worse. See, right now, at the physical level of these systems, there aren't too many options. So physical database design is not too hard. But as more and more options are put in at the physical level, the new structures like hashing and so on, that is going to get more difficult. And the requirement for this is going to increase. As for the logical design aid, well, here I'm very skeptical. I've never seen a logical design aid where it wasn't easier just to do the design than it was to learn how to use the design aid. And the point is that the input to the design aid has to come out of the designer's head, and if the designer has all that information, usually he could just do the design. Except maybe in very complex situations. It might be nice sometimes to have that, but it is not nearly as important in my book as that is. Last.
Up the back, Chris.
Yes. The comment is, and I agree with the comment, it may be nice to have a tool that helps you design the database, but isn't the real problem figuring out what the demands on the database are going to be, what queries you want to run and what their frequencies are. Yes, that is a real problem. I have nothing to contribute. My last technical foil, the miscellaneous topics. I prepared this foil in IBM. It was originally called long-term developments. The lawyers didn't like that. They didn't like developments because that smacked of pre-announcing systems. Long-term was all right, except that it suggested that other things were short-term. So miscellaneous topics. Very briefly, higher-level interfaces. Nobody would claim that languages like SQL and Quell and so on are the languages that everybody should use to talk to a database. You know, they still require a certain amount of programming knowledge and expertise. What we need is higher-level languages on top, which use the functions of those languages as a common core. So there are systems around today that already have fill-in-the-blanks kind of languages, forms languages, which are very nice. Ingress, for example, has a very nice forms front end. There are natural language interfaces. For example, IBM recently announced a tie-up with the Artificial Intelligence Corporation to market a product called Intellect, which is an English language front end to database systems. Ted Codd, who was the guy who invented the relational model, did some work on natural language too, a system called Rendezvous, which I wish I had time to tell you about, but I don't. Distributed databases, it says next foil, we don't have time for the next foil, but the relational model is good for centralized databases. It is essential for distributed databases. All the distributed systems I know, the prototypes that is, that are being built, all use the relational model as a basis, and there are many reasons why that is so. One of them is this optimizing again. It's very important in a distributed system to choose the right strategy. I can give you a trivial example of a query which uses data at multiple sites, and depending on the strategy the system uses, the response time for that query can be anywhere from 1 second to 2.3 days. So optimizing is a requirement, and that says you have to have high-level interfaces. There are many other reasons too why relational is essential for distributed systems. New kinds of data. The relational model is very good at handling character strings and numbers, and dates and times in some systems. And an interesting question is, can we extend the model to handle new kinds of data like text and images and icons, things like that, retaining the conciseness and precision and elegance of the model? And a lot of people are looking at that. A closer relationship between databases and programming languages. Before ever I was in database, I was in programming languages, and I regard it as rather sad that many of the things that the database people have discovered, the languages people already knew. There really has been sort of parallel development with not too much cross-fertilization. I would like to see some. It is beginning to happen. There are also things that the database people that the languages people don't know as well. I think, for example, that we know more about concurrency and recovery and things like that. Semantic modeling. This means elevating the level of the interface. When we say that, for example, an employee is represented by a row in the employee table, that's not true. That statement is inoperative at this time. Typically, an employee is represented by 1 row in the employee table, and 10 rows in the employee benefits table, and 3 rows in the employee dependence table, and 27 rows in the employee job history table, and so on and so on. And all of these things together represent the real world entity, if you like. And it would be nice if the system understood that all of those things were related. Foreign keys are important here. And there has been some work on elevating the model. Ted Codd again has a thing called RMT, an extended relational model, which as a matter of fact he first presented in Australia about 3 years ago. It has not been implemented, and in fact is still in somewhat of a ragged form, but it gives some ideas on how we might elevate the level. So to conclude, this has been a status report on relational systems. I didn't talk about the 3 generations for time reasons. I told you the basic relational model, what it was and why it was what it was. It has 3 components: structure, integrity, and manipulative part. Please, it has 3 components. It is not just structure. I looked briefly at some current systems. That led into the question, what is a relational system? The proposal is, it is a system where the user sees tables and nothing else, and he has at least select, project, and join unconstrained, no physical predefinition required. And then briefly I looked at some possible topics for investigation. Under user interface, the number 1 message, in fact the one message I like you to have when you go away from here, is that foreign keys are important. Foreign keys. I looked at some other things too, like outer join. Implementation, I think things are just going to get better and better and better. Tools and aids, I think a physical design aid is important, a logical design aid less so. Long term, I very briefly sketched a couple of things like semantic modeling and distributed databases. What I expect to see over the next 5 years or so is consolidation of the existing relational products. I mentioned there are 40 or 50 of them. They probably will not all survive. The good ones will survive, the others will go to the wall. But I also expect to see diversity. Building on a solid relational base, we're going to diversify into the electronic office, distributed database machines, database operating systems, distributed databases, higher level semantic models, etc., etc. So I guess the final message is that relational systems are here to stay. They are the way of the future, if you like. The end. Any questions?
Chris, just before we close, there was one final question, if I could take it in the far back corner. The gentleman in the far left, as I'm looking out. Did you still have that question? Did you have a question? No? Okay.
There's one here. Yeah. Go.
Could you just speak on the progress of the task group that you mentioned earlier to present a model to ANSI, and how do you see that going?
The question, if I understand it, is what is the status of the... Do you mean the database task group of Codicil?
Well, you mentioned that there was a database task group looking to present a relational model.
Oh, okay. ANSI has a database committee. It's called X3H2. They have a charter to produce a relational standard. I have monitored their work somewhat. They took IBM SQL as their starting point. They are quite a good bunch of people, technically speaking. They are very motivated, and they've made quite a few changes to IBM SQL so that if they come out with a standard, it will be different from IBM SQL, but it will be a SQL-like language. They expect to go for public review about a year from now, and it's quite likely they'd even beat that. You know, if you look at what happened on the network stuff, they started work on a network standard in 1971. They still don't have a network standard in 1983, so you might think, oh, it takes 12 years, who cares? But there are a lot of differences in this relational one. Number one, I sincerely think the people are better than the old people. Number two, they're more motivated. Number three, the base document, technically speaking, is far superior to the other base document. There were some holes to plug, but not nearly as many as there were in the old codicil stuff. So it's quite realistic to expect a proposal about a year from now.
Thank you, Chris. Last night our guest speaker spoke jokingly that he thought that Liberty was supported by IBM technology, but then he and I both admitted that it was really a battle between two crews, one of which had the better skill on the day. I think this morning we've been fortunate enough to be part of an informative and entertaining presentation by an equally skilled person who obviously knows, lives and breathes this subject. On that basis, Chris, I would like to present to you on behalf of the Australian Computer Society with this small token of our appreciation of your effort in putting your speech together and presenting it to the